that concludes our discussion of the interactive boundary layer theory. So this is a very simple case in which it shows that coupling is going to prevent the singularity from happening. But this is the simplest type of external flow we are considering, right? In a more realistic case, the external flow solver may be a potential flow solver, like using panel method. It could also be a grid-based method, like solving Euler equation that governs inviscid flow, or solving the full potential equation. And in these cases, we have to either, there are two possible ways to deal with the incorporating the effect of the displacement thickness into the flow solver. The first method is to actually change the grid. So let's say this is X, this is Y, and if this is the delta star, the external flow solver is simply going to treat the delta star being like a wall. Okay, so instead of having a wall over here near the surface, it thinks that the flow solver thinks that it has a wall that is slightly displaced from the surface, and how much it is displaced comes from the boundary layer solver. So this is method 1, and there is an alternative method that does not require you to change the grid. So you still have the grid being conforming to the actual physical wall, but you change your boundary condition. Instead of having a boundary condition that is velocity dot with n equal to 0, you're going to change your boundary condition to velocity dot n now is equal to what? Vi, right, which is in this case is d delta star dx. So d delta star dx times my u, right, times my tangential velocity. So this term gives you how much the boundary layer is thickening, and the fact that u dot n is equal to this comes from the mass conservation equation applied to a boundary layer profile.